Welcome back to our Python Quickstart tutorial. In this video, I will show you how to do linear algebra using Numpy. Hello, welcome back to our second part of the introduction of Numpy. This part is really helpful when it comes to working with vectors and matrices. Why are we actually working with them? Because they represent typically linear systems of equations that we have to solve or where we have to find eigenvalues, eigenvectors, and so forth. These are the most common operations. These operations are included in the Numpy module in an extension, and that's the Numpy linear algebra. I recommend you Google Numpy and look at the linear algebra package. It's very comprehensive. Numpy provides all those operations for integers and floating point numbers. And there is a similar package that's called SciPy that includes those for complex numbers. Since these packages are fairly big, you may eat up too much memory on your computer if you just say load everything. So these extension packages are not loaded automatically. If you need something, it is typically advised to only load exactly those things that you need. And one way of doing it is, for example, I say from the Numpy linear algebra collection, import the solve method only. So that only imports the matrix solver. And I want to demonstrate its use by simply solving that system of equations here. It's a 4x4 system of equations. And I named the values already x0, x1, x2, x3. That's the naming convention, like the indexing in Python, C, C++. I didn't start with 1. I hope that helps us a little bit understanding things. So first, I have to define these two. I take the matrix, and the only thing, what's the trap here is, keep in mind that you are building it row by row. So it's the first row, the second row, the third row, and the fourth row. The right-hand side is a 1D object, and that's the nice part. If you use matrix, you need to define it as a matrix, but if you use the array, it's a one-dimensional object. There is no difference between row and column. And then if you have a system, AX is B, or in this case, Y, then we just call that solver that we loaded up in here. So we have that solver and we load. So let's check. First, I define my objects and load the solver. Then I solve and assign the solution to X, and I can do a print for a pretty print. And it looks like we get floating point numbers. And I bet if I try that, hey, that looks like a 0. This looks like 2/3. 10 to the minus 17 looks like 0, and that looks like minus 1/3. We could try and play it. I don't want to do it right now. I leave it for you to experiment. A different application that is very common is the eigenvalue problem. So typical eigenvalue problem, A as a matrix times eigenvector n is equal to a scalar times n. So it's basically saying an eigenvector is a vector where the linear map only stretches it, but does not rotate it. Or you may know this as A minus lambda 1, determinant is 0, is the same problem. And, the way how we work this is as well the linear algebra package. It has an eigenvalue solver. And one way of using it in the short form, if you need it only once, instead of saying from Numpy linear algebra import eigenvalue, we can directly call it as numpy.lineal.eig. So that's a different form to get it. And it says, give me an eigenvalue analysis of the matrix A. A was the 4x4 that we just defined above. and the return comes as eigenvalue and eigenvector pairing. So if we execute this, let's check. Lambda comes back as a 1D array. It's first eigenvalue, second eigenvalue, third eigenvalue, fourth eigenvalue. I'm not sure if it's always sorted that way from largest to smallest. They may be in any order. I would be careful about that. And if I look at my vectors, it's the first eigenvector is the first column, second eigenvector is the second column, and so forth. The first column goes with the first, second column goes with the second, and so forth. So what do we do with this? I just say, I want to understand that the numbers are correct. How about I plug that in and I want to test it? And that's the other thing. How do you test things if you have these monster arrays of numbers? I simply want to test it and say, let's check. If it's an eigenvalue problem, then A times the eigenvector minus eigenvalue times eigenvector should be a zero vector. I don't even want to look at components. A zero vector, I can take the norm of the zero vector should be a number 0. So what I'm doing is I want to loop. I have that 4x4 matrix. I get 4 eigenvalues, 4 eigenvectors. I want to check for every eigenvector for every eigenvector that this equation is satisfied. So here I do a little bit quick and dirty. So I really loop from 0 to 3. These are my indices. Okay, fine. I get my indices. I loop I is now the 0, first, second, third eigenvector. Then I need to compute this. A, I have the nth eigenvector is out of that vector array for all of the first index and the index I. And that's built exactly the way you're familiar with from MATLAB. It says the entire column with that index I. So that could be 0, 1, 2, and so forth. This is my eigenvector Ni. I have that eigenvector Ni here as well. So that's the eigenvectors. That's a 2D array. The eigenvalues is my lambda is a 1D array, so I have only one index in here. So I have W is this vector A times Ni minus lambda I Ni, and I want to test it that the norm of that vector is 0, and the norm is the square root of the vector dot itself and the linear algebra module. So not Numpy, but the linear algebra module in Numpy has a norm function that takes that vector W. And I just say, okay, I want to plot and say the I solution has which norm. Let's just try that. And yes, beautiful. We got that done. Everything is numerically 0. I just want to show you what if we mess that up. How could we mess it up if we take the rows instead of the columns? Yeah, so it's like it's transposed. If I do that wrong, I comment that out. And we see that the test would immediately tell us, oops, something's wrong if I do this. That's not 0, that's 4, 4.8, 3. So clearly, using the wrong indexing is wrong. That test works. It tells us the right answer. There are a few other tips and tricks that I have here in that demonstration. I don't want to go much further. I really want to just emphasize, check Numpy, the linear algebra, and the SciPy reference for more information. SciPy, I mentioned, has things like this for complex stuff, but SciPy also adds sparse matrices. So if you have really a lot of zeros in your matrices, you may get quite a bit of performance improvement by switching to sparse matrices. It has Fourier transformation, FFT. That's for everybody who's doing spectral analysis, any mapping. It has a lot of statistics functions where you can get random variables in different distributions. It has optimizations functions. It has image processing and signal processing routines that, depending on where your research takes you, can be extremely beneficial. I want to keep that short. I want to stop here and switch back to our live sessions.